So let's start with our first case. We're going to simulate a rectangular shaped pipe in OpenFOAM. Here you can see our geometry. On the left we'll have our inlet. We'll specify a certain velocity, and on the right we have our outlet. So to get started we need to copy a tutorial from OpenFOAM and edit it. So just go to your OpenFOAM folder, enter tutorials, and choose incompressible, because we're going to have a stationary, incompressible and laminar flow. So just choose EcoFoam, which means incompressible foam, and choose the cavity tutorial. Copy it to your desktop. Copy and paste. Alright, so we copied it and we have it right here. I'm going to rename it to lecture 1. Now I've opened up the folder lecture 1, and you can see 3 subfolders. The first one is the 0 folder. It contains 2 files in our case, P for the pressure and U for the velocity. Here we specify our boundary conditions and our initial conditions for the field. But the first thing we need to do is to edit the geometry, and I'm going to show you how our geometry looks like. I prepared something for you, so you've already seen this picture, and OpenFOAM only deals with 3-dimensional geometries. So basically we have to define something like this, a box, a 3-dimensional box. So on the left you have our inlet and on the right our outlet. We're going to use the block mesh command, so we need to specify some vertices. We're going to specify them like this. The first surface will be 0, 1, 2, 3, and the back surface will be 4, 5, 6, 7. So it looks like this. Okay, now you enter the constant folder of our copy tutorial and you enter polymesh. Just delete this file boundary and open up the file blockmeshdict. This is our blockmesh dictionary, so you need to edit it. The first line is convert to meters. This will convert all your lengths into meters with a certain scale. So we're going to choose let's say 1. So everything will be in meters. Now we need to specify our vertices, as I already said. And yeah, well, let's look again at our geometry. It looks like this. So the first point is 0, 0, 0, like this. Then we need a length. Let's say it will be 10. So the second vertex will be 10, 0, 0, 0. Next one is number 2. It will be 10, let's say 3 and 0 for the z component. 10, 3 and 0. Now the fourth one is, or third one, was 0, 1, 0, 3, 0. And for the others I'm going to just copy and paste it and add a z component like this. Now we need to specify the blocks. We only have one block. It is hexahedral. Here you put in all the vertices which define the block. The next vector specifies how many cells are used in which direction for meshing the mesh. We're going to need 200 cells in the x direction, 200 cells in the y direction, and only one cell in the z direction. So we have a two-dimensional simulation. The next keyword is simple grading. Just leave it with 1, 1, 1. It makes it is used for refining the mesh next to edges, but we don't want anything graded. We just want a uniform mesh. And then you're going to read edges, but just leave it like it is. And then boundary. In boundary, we're going to define our boundary surfaces. So the first surface will be our inlet. We're going to rename it to inlet, change the type to patch because it's not a wall, and then you need to put in the vertices. Let's have a look at our geometry. The inlet is this surface, and you need to specify it so that the normal vector shows out of the surface. So in this case it will be 7, 3, 0, 4. 7, 3, 0, 4. Now let's have a look at our fixed walls. Let's rename it to top and bottom wall. And we have two walls. The top is 7, 6, 2, 3. 7, 6, 2, 3. And the bottom will be 0, 1, 5, 4. 0, 1, 5, 4. Delete the third line. And what do we need next? Our outlet. It's also a patch, so we're going to define just copy the inlet, rename it to outlet, and the surface is 2651. 2651. And now the last one is front and back. It will be a empty surface because it's a two-dimensional simulation, so it has the type empty, and the faces are 3, 2, 1, 0, or 0, 3, 2, 1. It's correct, and 4, 5, 6, 7. Yeah, that's it. So save the file. And now we're ready to set our initial and boundary conditions. Go back to your case folder, enter the 0 folder, and open the two files P and U. Okay, the P file is our pressure file. First thing is dimensions. Leave it as it is because yeah, it's already the right dimensions. The internal field is set to uniform 0, so all the cells will have the value 0 in the beginning. And now you need to define the boundary field. So here you put in all your boundary surfaces. Our first one is inlet. The type will be 0 gradient. Second one is outlet. Define type fixed value, and the value will be uniform 0. So we have 0 pressure on our outlet. Front and back is empty, and our third surface was called top and bottom walls. So top and bottom walls, and copy and paste 0 gradients. Save it, and let's enter our U file. It defines the velocity, and we're going to have a uniform velocity of 0 in our field for the initial conditions. And let's copy and paste this thing like this. Our inlet will be a fixed value, so we have a fixed inlet velocity. Let's make it, let's say 10 in the X component and 0, 0 for Y and Z. Outlet is 0 gradient. For the walls, we'll have a no slip conditions. So next to the wall, the velocity is 0. So let's make it fixed value. And 0. And front and back is already empty. Save it. Let's have a look at the other files now. So which are left is transport properties. In our transport properties, we're going to define a new. This is the kinematic viscosity. So you can set it to a number so it matches a physical fluid like air or water or oil or something like that. But we're just going to leave it at 0.01 meters, square meters per second. Okay, and the last folder is system. It contains 3 files, which is control dictionary, finite volume schemes, and finite volume solution. Finite volume schemes contains the discretization of the Navier-Stokes equations, but if you don't know what you're doing, just leave it as it is. It would require too much background knowledge to explain to you which settings to use, so just leave it as it is. And there's also the FV solution. It specifies the solvers and preconditioners for the fields. Yeah, the same as for finite volume schemes. Just leave it as it is. Maybe one thing you can play with is the tolerance. It defines how accurate your solution is, but the standard settings are pretty fine. So the file we need to edit is the control dictionary file. It's quite important, so let's have a look at the settings. So the first setting is application, EcoFoam. We're going to use the incompressible foam solver. Start from is the starting time. Start time is 0, so it will start from 0. Stop at the end time, and the end time is 0.5. Let's change it to, let's say 1 second. Delta T is the time difference between the steps. Let's make it a millisecond. Write control is set to time step, and it defines how often OpenFOAM saves results. So we're going to make the write interval to 1000. So every 1000 delta t's it will save our field, so we can have a look at it and analyze the solution. So we're going to have the solution every second, since 1 millisecond times 1000 will be 1 second. Yeah, don't change purge write 0, write format ASCII, write precision 6, write compression off. time format general, time precision 6, and runtime modifiable true. Okay, everything is fine now, and we can run our simulation. Now all files are set up and we're ready to start our simulation. So open a new command line. Change your folder. And the first command will be block mesh to execute the creation of our mesh. So we type in block mesh. Our mesh is created. You can type in check mesh to check if everything is fine. So okay, our mesh is okay, which you can read here. And now we're going to start the job. So you type in foam job echo foam, and the output will be saved in the log file, which is very important because we need it to analyze the convergence of our solution with the residuals. Hit enter and our simulation starts. You can open up the log file, and yeah, you can see that the iterations have started. You can refresh the file and you see that the time is progressing and the solution is calculated. So we're going to take a break here, and in a couple of minutes we're going to continue. Alright, now the simulation has ended after a couple of minutes, maybe half an hour, depending on how fast your computer is. And now we have a new folder 1, which contains our results, and the file log, which contains the log of the simulation. So let's have a look at the log. It goes up to 1 second because this was our simulation time. And now let's check the residuals. They give us information about the convergence of our solution. So open the command line. Change your folder. Lecture 1. Okay, and just type in foam log. So the log file will be analyzed. Right, so a new folder is created, logs. It contains all the residuals and other stuff. And now we need to plot the residuals so we know how our solution has changed over time and if it's constant now. So we're going to use the GNU plot for this. GNU plot, set the y-axis logarithmic with set log scale y, and put in this line plot, and then the plot of the files, which is p0, the pressure residual, and ux0 and uy0, which are the velocity residuals. Hit enter, and here you can see the residuals. This is our time axis, so from 0 to 1 second the residuals have fallen, but they're not constant yet, so our solution has not converged. It is converging since the residuals are falling, but we need to simulate further to have a stationary solution. So what we're going to do is close it, exit GNU plot, open up the system folder, open up control dict, and we need to change our end time since 1 second was not enough. Change it to, let's say, 10 seconds and run the simulation another time. So we're going to save it. The mesh is already there, so we just start a new job, foam job, echo foam, save it into log, and we'll continue in a couple of minutes when the new solution is ready. Alright, now we have 10 seconds of physical time simulation, and we're going to have a look at our residuals now to check if our solution has converged. So type in foam log on the file log, so we get our residuals out of the log file. It takes a couple of seconds to generate them. And now open up GNU plot, set the y-axis logarithmic, and plot the values. Okay, here you can see the residuals for P and the pressure P and our velocities, and you can see they dropped, and then they have a constant value. So our solution isn't changing anymore, and it has converged, so we can use our results to analyze them. For analyzing them, we're going to use the program paraview. You started with the command paraview. So paraview opens up, click apply, and yeah, now we can check the velocity. Here you can change the time step, so this would be the initial time, and we're going to jump to the last time step 10, which is 10 seconds. Rescale data to range, and you can see the velocity distribution in our channel, in our pipe. Yeah, it's pretty simple, and we have our inlet velocity. Let's have our scale here. Yeah, we have our inlet velocity of 10 meters per second, and here you can see the boundary layer which gets thicker, and yeah, nothing special. If you want, this is the interpolated U field. You can use this one, which is not interpolated, but it doesn't change much because we have a very high resolution. Let's check our mesh. So now you can see the surface with edges, and we can zoom, and yeah, the cells are really small, so we have a really nice resolution. And yeah, you can also check the pressure field here. So let's have a look at this one. Surface, so we have a pressure gradient. Yeah, here the pressure is 0, and here it's higher, and yeah, it's a linear gradient over our field, as you can see.